Okay. Okay, so today is a bit of revision again, but it's leading us now into our first set of discussions, which which will eventually lead us to the fast Fourier transform. Okay, today we're going to talk about the continuous time Fourier transform, how we got there, and we'll lead on to some other matters from that. If you remember, again, the whole question of frequency domain analysis is an incredibly important, what shall I say, discussion in almost all electrical engineering problems and situations. Once you have a communication channel, then how much frequency you can get, what we also know as the bandwidth, is incredibly important. And those communication channels can be from very low bandwidth, very low frequencies, all the way up into the high gigahertz ranges. And we also know some of the typical analyses, for instance, speech recognition. We're using Zoom right now, and there's an AI assistant that is, if I were to activate it, would attempt to track what I'm saying and what anyone else's contributions are, and give me a printout at the end. It is using, among other things, frequency domain analysis in there, first off to identify the speaker, and then to try to transcribe what I'm saying. Some other uses of it, and this is you could think of any number of situations like that. The tone controls on audio equipment in your car, at home, wherever you have it. Those of you doing power systems, the harmonic analysis of power systems is incredibly important, because harmonics in power systems generate wasted energy and heat, which is what you don't want. Load disaggregation is sort of the sort of flip side application of harmonic analysis. So for instance, like in your house, if you wanted to see what equipment was using what power, then you can look at the sort of signature of the power, the current waveforms in the house, and use signal processing and frequency domain analysis to separate, let's say, the dryer from the water heater, from maybe the pump motor, and so on. And on an industrial scale, of course, you could do that at in a much larger scale. We spoke about the stock market. We mentioned audiology, that's sort of hearing implants and the like. Image processing, we mentioned. We spoke about electric vehicles and the like, and the fact that even toys, right? Drones and quadcopters and remote control vehicles and so on. All of them use some kind of communication system, which means that there's some bandwidth requirement, which means that whoever was designing it had to do some sort of frequency domain analysis in the initial stages anyway. Right? We remember that from our previous discussions, that the frequency content of a signal is what we call the spectrum. And the term came from, of course, the analogy to light, that when light passed through something where it was diffracted, that you got a whole range of colors in it. And of course, because the frequency content is spectrum, how we get the frequency content is spectrum analysis. In the continuous time world, there are some very expensive pieces of equipment called spectrum analyzers. And we actually have a couple of them in our labs downstairs in the year 2 lab. There's one down in the back that Professor Gift was using up until fairly recently. It is really a very expensive oscilloscope, but it also has a lot of analog filters in it. So when signals come in, it will use the filters to break up the signal into its various frequency components, and then display it on a moving screen, like an oscilloscope type screen, and so on. It's very expensive because it's working on continuous time signals. And as we saw last week, the continuous time signals, processing them, while you can't do it with your electronics and your continuous time electronics, manipulating it is not particularly easy. So in this case, if you want to do analysis, what you have to have is a set of analog filters that you could switch around the bandwidths and so on. And as the signals come in, they go through these circuits and are continuously analyzed. We're going to find, well, there's a simpler way of doing that with some exceptions, which is what this class and this course is about. Right? Remember this is all sort of revision, good, bad, or indifferent. It might bring back some bad memories for some people, some better memories for others. Remember, this whole thing started off because there was something that was discovered some time ago, that a periodic signal, right? And remember what the periodic signal is, right? We spoke about that last week, right? So a periodic, and right now we're in the continuous time domain. A periodic signal can be expressed as an infinite sum of orthogonal functions, fancy mathematics. Orthogonal functions are just functions where if you do the cross product of the function, the answer is 0. Sine and cosine are typical orthogonal functions because they are offset by 90 degrees or pi over 2 radians. So if you were to do a cross product of them, like from your vector maths and so on, the answer is 0. And there are many other functions that are in fact orthogonal, but the simplest ones are the cosine and sine. And if you take a continuous time periodic signal and you express it in terms of a sum of sines and a sum of cosines, then we produce something that is named after its discoverer, which is the Fourier series. All right, and each sinusoid and the sinusoid term here is a generic thing, right? This is sine or and cosine and or, right? You get multiples of the fundamental frequency. So there's a fundamental frequency component in here, and then you get an infinite sums of integer multiples. So if f0, 2f0, 3f0, 4f0, and so you could go on. Yeah. And again, we saw, like, for instance, if I have a square wave or rectangular wave or something like we have here on the left-hand side, right, that it can be broken up into sums of sinusoids. And notice, remember the sinusoids, there's a 0 hertz signal plus all of the rest, right? So this is the DC plus the fundamental plus twice the fundamental plus 3 times the fundamental and so on, right? In this particular case, they're just showing you that even the first 4, the DC plus the first 3 harmonics, 1, 2, and 3, that if you add them up, already after the first 4 terms, you're starting to get something looking like the original signal. Okay, so we know the thing works, but you have to, the big thing here is, which is why it's difficult to compute, is that we have to have an infinite sum. So you have to keep going on and on and on. Yeah. Right. There's a number of common ways of describing that. And way back, you know that there's the trigonometric form, which literally has a set of sine functions plus a set of cosine functions plus a DC. But as we saw, there's a way through the complex exponential E that you can relate sine and cosine through Euler's formula. So once you do that, you are able to get the Fourier series into a complex exponential form, which looks like the 2 equations that we have below. So here's your infinite sum series here. So this is the Fourier series. And here are the coefficients of each component of that. Okay, so this is my continuous time signal. And this now, if I expand the sum here, right? It's going to tell me all of the various values as a function of its fundamental frequency. And k, of course, is going from minus infinity to infinity. Of course, we don't have minus frequency components. It just comes about because of the relationship between the complex exponential and sine and cosine. It's a mathematical artifact. Okay, so after if you were to expand everybody, all of the negative terms or the imaginary terms and so on will cancel out. Okay, and you get the complex exponential form. And why we sort of use this in our work was that because this form, this equation looks very similar to the Laplace transform type of equation, right? Laplace transform here, the limits of integration are different, but it's e to the minus j k omega naught t. Remember, the Laplace transform is e to the minus st. So it will jog your memory anyway. Yeah. And once you use it, you have the complex coefficients which give you for each sinusoid or cosinusoid that you have inside of the Fourier series, what is the amplitude? And of course, what is the phase? Okay, that e to the j, remember, j is, if you remember, the e is cosine plus j sine, right? So that there's a phase angle between the sine and cosine, depending on the values of both functions. So you get a magnitude and you get a phase out of this, right? And because of that, the plot of the magnitude is called the amplitude spectrum. So if you plot that, you actually get to see for any continuous time signal what the variation of frequencies are and how the phases of those frequencies are as well. Okay, and remember this thing in purple downstairs, that k assumes integer values so that the amplitude and space and phase spectra appear only at discrete points, which are multiples of omega 0. Okay. So if you recall, well, first off, any questions on this? Everybody all right so far? Let me know. You have to say something because I can't see the chat. You right? Yes, no?
Yes, sir, we good.
Okay, so one person. All right. Okay. And when we did that, we looked at an example here where we had a pulse, and the pulse had a period of t and a width of a. And if you did the calculation for this, you got that the Fourier, the complex Fourier series coefficients looked like that, a sine k pi a over t over k pi a over t, which we saw was something called a sinc function, right? You could check back your notes on it or try the integration just for the fun of it to see if you could get it into this form. This is the sinc function is anything, so sinc x is sine x over x, right? It's given a name, the sinc function. So that if you were to plot the spectrum of this rectangular wave, if you were to plot that, you get a spectrum looking like what we have up on the screen. Couple of important, remember that the spectrum, the signal coming in is continuous, right? Remember the signal, what did we use for the signal here? Ft, okay. So Ft is continuous. Oops, let me scratch. Ft is continuous, but the spectrum of Ft is discrete. Notice it happens at multiples. This is the DC value here, right? So this is sorry, DC. This will be omega 0. This will be at 2 omega 0, 3 omega 0, etc. Right? So that an important thing is that for the Fourier series, and a complex exponential Fourier series, the signal is continuous, but the spectrum is discrete. It only occurs at multiples of k. So there's nothing between DC and omega naught, nothing between omega naught and 2 omega naught, okay? The line spacing, if you do this, the spacing between each of these components is pi a over t. And the zero crossing points here are multiples of m capital T over A. Remember, T is the period and A is the, T is the period here, and A is the pulse width, right? So right here we have it that a periodic signal, and we'll come back to this thing in a little while, a periodic signal has a discrete spectrum. And if it sounds strange, you could go back to think of a sinusoid. If I give you a 60 hertz signal, and I'd ask you, what is the spectrum of that 60 hertz? The spectrum of a 60 hertz signal will be, if I were to plot the spectrum omega against the magnitude of CK, right? Then for 60 hertz sinusoid, a pure signal coming in here, you just have one, you're going to have one signal here, right? And that will be a 2 pi, well, if we go in with omega, it will be 2 pi by 60. If you're going with F, then this will be just a single line at 60 hertz. So the continuous sinusoid has one spot. If I were to have a sinusoid that had two frequencies, then you would have just two frequency components, all right? So it's not so strange, but just remember that thing that a continuous time signal has a discrete spectrum. Right, so what happens as the period increases? If you go back here, notice that the line spacing is pi a over t. If the period increases here, if this is increasing, then the line spacing is going to get smaller and smaller. Remember, the line spacing is this, right, between two consecutive points. So if the period starts to go up, the line spacings start to get closer and closer together, right? As t increases, the line spacings decrease. So the spectral lines get closer and closer together. The zero crossing points, let's look at that now. Where the points, these points here, this point, this point. The zero crossing points are multiples of t over A. So as t goes up, the lines start to get closer and closer together. But as t goes up here, these zero crossing points, because mt over A will go up as well. So the zero crossing points start to move further and further away. So as t increases, the lines get closer and closer together, and the zero crossing points move further and further apart. So in other words, the spectrum starts to flatten. And if I go back to my line here, if points 1, 2, and 3, so if this starts to move so, then the spectrum starts to do something like this. And then the more I make t, then it will go. Right? Make sense? Everybody following?
Yes, sir.
Nice. Right? So as the spectral lines get closer and closer together, and the zero crossing points get further and further apart. So keep that in mind. But what that means is that if let's go to use this diagram. If the lines get closer and closer together and starts to flatten out, then what am I saying here? T here is moving further and further apart, so that the signal, this ft, is now looking like this. And then if I were to go, right, as t gets bigger, then this would move out. So you would still have the point here, and then this other one will be here, and then the other pulse is here. So this is what it's looking like. And then eventually, right, what you get is that this spectrum now starts to, these points get close, so close together and moving up apart. So the spectrum starting to flatten out, right? We're going to use that a little bit in a short while. Right. Now, the Fourier series applies to a periodic signal. But almost all the natural signals that we encounter in the real world are not periodic. And sometimes it may be periodic for a short time, or it may be just be a sporadic burst or something like speech, for instance. Depending on what someone is saying, that signal, the speech signal itself, will not be periodic. So what do you do? What is the period of a non-periodic waveform? Well, remember what we did is that we took the approach that, okay, a non-periodic waveform is one where the period is so big that it basically doesn't repeat itself. So what we do is that we take a periodic signal and we stretch the period so big that the period is infinite. So in our sort of way, which was a sort of logical approach to it, we assume that a non-periodic signal was just a periodic signal where the period was huge. So if we assume that t, which is the period, goes towards infinity, then we can modify our equations a little bit. As t goes to infinity, omega 0, which is the spacing between the components, remember that, right? As t goes to infinity, the spacing, which is 2 pi, which is pi a over t, gets closer and closer together. So in other words, the spacing between the omega naughts start to get smaller and smaller until the space between them is so small that you can't distinguish it. So the omega 0 now drops, the actual value of omega 0 now becomes so small, k omega 0 now becomes a continuous function of omega. And the coefficient function that we have, which was a function of k, because the function is now a continuous function now, has gone from c subscript k to some continuous function of omega. So that the equation for the coefficients of the exponential Fourier series here was, once we start to make t very big, the k omega becomes continuous because the spectrum becomes continuous. The ck now, instead of a function of k, now is a function of a continuous variable. And then, of course, the period now, because the fundamental frequency and so on has now dropped down to something very small. Instead of this omega 0 and so on, the increment between everybody is delta omega now, right? We now have it as 2 pi as delta omega over 2 pi, and we get this expression looking here, looking like that. Right? So what we did, remember we went through this in 2011, some time ago. So this, what we have up top now, is nice, but it still is a little bit unfriendly for us. So what we do, well, just some points here that we now have an infinite number of k values because the thing is continuous. So therefore, C of omega is a continuous variable. T is now infinite. So because of that, we can now put the expression in this form. And we made one other little, okay, before I comment on that, right? So a periodic signal, which is what we had started with, has a discrete spectrum. A non-periodic signal has a continuous spectrum, right? Remember how we get there? The period, you increase the period, so the spectrum spacings get smaller and smaller until in the limit, the spacings become continuous. And then if you juggle around and redefine a little bit, we took the expression for C omega and we said, okay, if we let C omega, 2 pi C omega over delta omega, we redefine that as some new variable called X omega. And we now call this whole thing the continuous time Fourier transform of xt. We didn't make much of a difference then, but we just used the term, the sort of blanket term when we were doing the class, that we call that now the Fourier transform. So if I give you a signal and ask you to find the Fourier transform of it, first you have to understand that the signal is non-periodic, and you could now apply this equation, which is, if you look at it here, that this equation here is almost identical in form to the Laplace equation, which is x t e to the minus s t e t, right? The Laplace equation integrates from naught, well, a little bit before naught to infinity. So there are some slight differences. But the core here, this and this are almost identical, with the exception that E is j omega in 1. So if you take, sorry, not E, S. If you take S in the Fourier transform and you replace it with j omega, not substituted because they're not equal, but if you substitute j omega for S, you can move from one transform to the other, right? And we saw, of course, if you have a transform, you must have an inverse. Whenever, mathematically, whenever you're transforming something into another domain, right? So we're going from time to frequency, you must have a way of coming back into the time domain. Otherwise, a one-way transform doesn't work. Okay, you're going to somewhere, you must be able to come back, right? It's not a one-way ticket, you must have a return ticket. So the inverse Fourier transform, which took the spectrum, so this one is taking a spectrum and giving you back time. All right. And of course, this is all well and good. Doing the integration is not particularly easy, as we saw. But in the general thing was that the Fourier transform allowed you to compute the frequency domain from a time domain signal. And the inverse transform allows you to compute the time domain from the frequency domain signal. The two of them are known as a Fourier transform pair. So like the Laplace transform, technically, you have a Laplace transform pair, one that takes you from t to s, the s domain, and one that takes you back from the s domain back to t. The Fourier transform, the continuous time Fourier transform, takes you from time to frequency, and then the inverse takes you from frequency back to time. We will talk about a relationship with the Z transform in a few lectures' time. Remember, the Z transform works in the discrete domain, but it takes you from time to some domain that is a function of Z. And the inverse transform takes you from Z back to the discrete time domain. Okay? And very importantly, for the continuous time transform, it applies to non-periodic signals. Okay? We will shortly talk about how do I apply the continuous transform to periodic signals, right? Because as we said, we kind of going back and forth here. The real world is continuous time. The real world may have periodic signals in them. A lot of times, if you sample things, the signal is non-periodic, so we can handle that. But what about if I have a continuous time periodic signal? What do I do? Yeah. So standard notation, right? The Fourier transform, the standard notation for the Fourier transform of some function xt is x omega or xj omega. This actually is a bit more correct because it lets you know that you're a function of j omega. It doesn't omit the x, right? The j is an important part of it, the complex variable, and the inverse transform, okay? Likewise, right? So it could be x j omega in here, right? Instead of x omega, you will see both of them, all right? The properties, because the form is so similar, many of the properties are similar. Because the Fourier transform integrates from minus infinity, and the Laplace transform, the single-sided transform, which is the one that we use, only integrates from 0, there are some exceptions. Okay, one of the big exceptions being that when you're dealing with a frequency domain, there's a DC component that exists inside of it. All right. Okay, so questions. Everyone following? Making sense? Anything not clear at this point? Most of this, if not all, was stuff that we did before. So I'm doing a little bit of revision here. Okay, so you're all right?
Yeah, yes, sir, clear enough.
Okay, so let's go on now and see. Talk a little bit about going from continuous time to the discrete domain. So we have the continuous time Fourier transform, which works. It works on paper because you're dealing with continuous time integration and the like. So if you have paper and some time and you're careful, you could work out answers, and then you could do you could plot the answers and so on. But it's not something that I could ask or could program something to do as yet. So let's talk a little bit now. We're going from that. We need to talk now about something called sampling. So what we just did allows you to go from the continuous time domain to the spectrum. We can't evaluate that CTFT as yet because we're dealing with a continuous time integral going from minus infinity to infinity. That there's no way I could program any computer to do that sort of thing. If we want to program it, we need to convert this into some set of numbers. And once we have it in the numbers, then I could do some work. As we saw from before, integration in the continuous time domain, right? If you make certain approximations, you could get the answers by doing summation with in the discrete time domain. And the more you sum, and the closer the spacing of the things that you sum, the closer it becomes to an integral. So how do we go from x t, which is continuous time, to xn, which is discrete? Do we have any restrictions? And then if we have xn, can I now put xn into my equation for the continuous time Fourier transform and get it to work? So let's answer some of these questions at least today, and the rest we're going to do on Wednesday. We've mentioned this a few times already. If I take a continuous time signal, then if I look at values at a specific time alone, I am doing something called sampling. How many, there are two things here. That how many samples, this thing about the specific times alone. So in other words, the original signal, I'll just draw it in red here. The original signal would have followed that. What I am doing is taking the values of the original signal here, wait a period, take a little value here, then take one here, and so on. That is the sample period. Sample is SLE period, right? Or remember, period and time are inverse. So if that was a sample period T, I could have my sample frequency, which is 1 over T, right? By my sampling, okay? Sometimes you see the word sampling interval being used. Just be careful with this, and we'll get to that in a little while, right? So most of the time, you sample sampling period, or better yet, sampling frequency. So you take the signal and you look at it at specific times alone, or at a specific rate. Now, that could work or it couldn't work. One of the problems is that, first off, if you sample right, like for instance, there's an image of a stock market, the stock price of some share, and I'm looking at it and I'm looking at it every week. So at week 3, it has some value, at week 4, it has some value, and so on. And if I sample correctly, the information is understandable, and the information used, obtained, is actually quite usable. So from this, I could see that whatever it is, reached a minimum here in week 4 and a maximum up here in week 9. What it can't tell me, if I'm sampling at a fixed rate, is what happened. Let's say week 5, this was Monday here. Week 4, this was Monday. And then week 5 here, this is the other Monday. So if you assume that nothing happens on a Saturday and a Sunday, somewhere inside of here, there were 5 days, Monday to Friday, variation that I'm not seeing. So I really don't know what happened. This could have done all sorts of things inside of here and landed back up at this value. Okay, so that's one of the things. If you sample and your sampling frequency or your sampling period is fixed, sorry, then if you're careful, it's a fairly good representation, but you really have no idea what went on in between. Okay, here is just going back to 2022, they actually sample the Dow Jones Industrial Average every minute. And in fact, I think they've started to shorten that, because you have people with algorithms and even AI algorithms now looking at this thing in fractions of a second and making trades and attempting to make trades and so on very quickly, which could lead to stock market issues and so on. If you all remember, there was a financial crash in 2008, and part of it had to do with the fact that computers were doing trading, and the computers were looking at the stock prices faster than the human beings were. So the algorithm started to do trading before a human being told it to do the trading, and that is the kind of issues that crop up from time to time, right? You can sample in a non-periodic way, right? So you could take the sampling time, you could take it at T1, T2, T3, which is a little bit different, T4, which is different again, T5, T6, and so on. The problem with this is that the information can't be interpreted easily, right? There's something that they call in advanced processing called adaptive sampling. Just to mention it, it means that if there are certain things that don't change too frequently, that you can look at it less often. And then if it suddenly starts to change, you crank up how often you look at it. All right. A little comparison between the non-periodic and the periodic is that the non-periodic, if you're not careful, there's a good chance that you could miss some information. And of course, you can't interpret the information that easy. The periodic snapshot, using the word of periodic sampling, is easier to interpret. But again, remember, if you take the wrong period, if you're sampling too large, then you can get some information that may go unnoticed, right? So the little trick is, how fast do I, the key is the sampling frequency. In other words, how fast do I look at anything? Remember from last week, we saw that sampling a signal is really taking the signal and converting it into a series of weighted impulses. So in other words, if I take a continuous time signal and I multiplied it by something called an impulse train, which is a function, which is a series of impulses spaced uniformly apart. And remember, we gave them the designation delta t minus nt. So every t, seconds, days, years apart, we put an impulse, and because of the shifting property of the impulse, wherever this is, wherever these are here, wherever these are located, this will pick out the value of the continuous time, and that is how we get our sampled signal. So you go from yt here to ynt. Right, and we mentioned that there. So ideally, an ideal sample signal, of course, ideal means that you take the continuous time signal, you multiply it by an ideal sample train. And remember what the ideal sample train is in time delta t. Remember, delta t is 0 with an infinite height. Okay? Then if you're lucky, you get this the sort of sample signal that you have here down below. Right. So if I were to ask you a question, I have the sample signal SNT, right, which is a series. This is the sampling train, which is a series of impulses. So this is my series of impulses going on, right? If I were to give you this and ask you, well, what is the spectrum of that? Well, to get the spectrum of it, because it's periodic, remember it's periodic, it has a period of t. Since it's periodic, I could use the continuous time Fourier transform. So this is the coefficients of the continuous time Fourier transform, and I just plug it into the expression. So if I do that, what I'm going to get is spectrum. Remember, because it's periodic, I apply the Fourier series to this. I get a set of values of C, N, or CK, depending. I'm using N here, right? So instead of CK, I'm using CN. So what I do, apply the Fourier series to this and work out the coefficients. And what you get, actually I had the animation a little bit reversed, is that the spectrum, when you apply the Fourier series to this character here, remember this is in time. When you do the Fourier series to it, right? So in here, you could put a little notation, Fourier IER series, right? So the spectrum here is also a series of impulses, and they are spaced omega s apart. So if the impulses in time were spaced t seconds, the spectrum of that is a set of impulses in frequency where they are spaced 1 over ts hertz, or omega s, which will be 2 pi over ts radians per second. So impulses in time transform to impulses in space. And if you want to figure out how that works, remember when you're evaluating this, that if I put an impulse here, right, then an impulse by this sifts out the value of this at the impulse. So for all of the D, actually I should use capital T here. For all of the DTs, so D at 0, it will sift out a value at 0. At T, it will sift out a value at capital T. At 2T, it will sift out a value at 2T. And remember, this is 2 pi over T, right? So you could see when you do that and the values that are sifting out, that when you try to evaluate that, you're going to get a series of impulses in frequency giving you a series of impulses, a series of impulses in time giving you a series of impulses in frequency. Yeah? This is something you, again, go back to the notes or just play with it with what you have here. Remember the sifting property of impulses. So it's not that you're going to evaluate that in integral. You can't. But because of the presence of the impulse, what it is going to do is to sift out the value every time you have an impulse. So impulse in time, the frequency spectrum of impulses in time is a frequency, a set of impulses in frequency as well. Okay? And remember what you're doing. Sampling, you go back here. I am taking a signal and I am multiplying it by a signal in time. When you okay, so let me just go here. So this is X. Did somebody say something? Yeah.
Yeah. So when I say, so for the sampling, when you're taking a continuous signal and you're multiplying it by basically a sampling time, that's the impulse train, right?
Correct.
Okay.
Right. So look at what we have. We have XT and we have ST, the sampling train. This down at the bottom is my X NT here, right? So if I take this and multiply it by ST and find the Fourier transform of this, multiplication in time gives you what in frequency?
Convolution.
Convolution. So that when I multiply in time, and remember again, this has its own spectrum. This has its own spectrum, right? Which is Sj omega, which is a set of impulses as we just saw. So if I multiply xt and st in time, I am in frequency, I have to find a convolution of x omega and s of omega, right? S omega is this. So I'm finding a convolution of x omega and s omega, which is now this, a series of impulses in frequency. So what is the implication of that? I will stop here and we're going to look at that tomorrow, please God. All right? So this is as good a point to stop as any. All right? So questions? What we started to look at, what we did the first half of the class was essentially a review, how we got to the Fourier transform, the version of the Fourier transform that we are accustomed to, the continuous time version, which is fine. Then we say, okay, we are in the discrete domain, so we need to sample. How do you sample? You take a continuous time signal and you multiply it by an impulse train. Great. But if I take that now, if I multiply it in time, now I want to find the spectrum of the sample signal. The original signal has a spectrum, that's fine. The sampling train, which is a series of impulses, lo and behold, that has a series of impulses in frequency. multiplication in time, which is how we get a sampling, transforms into convolution in frequency. So we now have a funny situation. By sampling, my frequency information is now, I now have a convolution of the spectrum of the signal that I wanted to sample and a set of impulses. How is that going to work? And this is where we're going to look at tomorrow, right? We'll put up this, hopefully the projector will work, or if not, I'll just draw the thing on the board, and we will see what are the implications of that, okay? And then we'll continue now. So now we sort of answering that question that I had in the end of the previous slide. What is the Fourier transform of a sample signal? Okay, questions? I'm sure you do, but at this point in time, if nothing right here, take a note of it, and when we meet on Wednesday, before we start, I'll clarify anything again, but look at it carefully, all right? Okay, so I'm stopping the recording now.